247 earthquakes in 72 hours. 60% of them inside Yellowstone's main caldera. The last time the United States Geological Survey upgraded Yellowstone's monitoring status this quickly, it was because magma beneath the surface had begun to move. That's not a guess. That's what the seismic network at the Yellowstone Volcano Observatory recorded over the past 3 days. And the numbers are still climbing as we speak. Thermal imaging cameras pointed at the geyser basins picked up something else at the same time. A 12% jump in discharge temperatures across multiple thermal features. Old Faithful, Norris Geyser Basin, the backcountry fumaroles near the Sour Creek Dome. All of them running hotter than they were a week ago. And while the public was watching the news for other things, the USGS quietly moved Yellowstone into a heightened monitoring posture. No press conference, no alert level change on the public dashboard. Just a procedural shift inside the observatory that tells you the people who study this volcano for a living are now watching it differently than they were on Monday. We pulled the real-time seismic feed. We lined it up against the August 1959 Hebgen Lake earthquake sequence, the last time Yellowstone went through a major unrest phase. And what we found suggests the next 96 hours could be the most important observation window scientists have had inside this caldera in more than 60 years. Stay with this one, because the pattern matters more than the headline. To understand why these 247 earthquakes matter, you have to understand what a normal week at Yellowstone looks like first. On any given week, the Yellowstone Volcano Observatory records somewhere between 40 and 100 small earthquakes. Most of them are tiny. Most of them happen along the edges of the caldera, where the crust is still settling from the last major glacial cycle. They're background noise. They're the geological equivalent of a house creaking at night. What happened over the last 72 hours is not background noise. 247 earthquakes in 3 days is roughly 4 times the normal rate. But the raw count is not the alarming part. The alarming part is where they happened and how deep they were. 60% of those events were located inside the main Yellowstone caldera, the 30-mile by 45-mile depression that marks the surface footprint of the magma chamber below. And the depths of those quakes cluster between 4 and 9 kilometers down. That's significant, because the upper magma reservoir at Yellowstone sits roughly 5 to 17 kilometers beneath the surface. In plain terms, those earthquakes are happening at the exact depth where the rock meets the molten zone. They are not crustal settling. They are not landslide tremors. They are pressure events. Something inside that chamber is pushing on the rock above it, and the rock is responding by cracking. The scientists at the observatory can tell the difference because the waveform looks different. A normal tectonic earthquake has a sharp arrival, a quick burst of energy, and then it's done. The events being recorded right now have a longer signature. Some of them show what's called low-frequency tremor, the kind of rolling, hum-like signal that happens when fluids or gases are forced through narrow cracks under pressure. That waveform is the fingerprint of an active magmatic system doing something it wasn't doing last week. To understand why this matters, we have to go back to August 17, 1959. That night, at 23 minutes past midnight, a magnitude 7.3 earthquake ripped open the ground at Hebgen Lake, just outside the northwest corner of Yellowstone National Park. It was the largest earthquake ever recorded in the Rocky Mountain region. It killed 28 people. It collapsed an entire mountainside into the Madison River and created Quake Lake overnight. And it shook Yellowstone hard enough to change the behavior of the geyser basins for years afterward. Hundreds of geysers that had been dormant for decades suddenly erupted. Old Faithful's intervals shifted. New thermal features appeared in places where there had been nothing but cold ground. The 1959 Hebgen Lake earthquake didn't just damage the surface. It physically reorganized the plumbing of the hydrothermal system underneath Yellowstone. And in the months that followed, the United States Geological Survey began modern monitoring of the volcano in a way they had never done before. Hebgen Lake is the reason the Yellowstone Volcano Observatory exists. Here's where it gets uncomfortable. In the 72 hours leading up to the Hebgen Lake event, the seismic stations that did exist at the time, primitive as they were, recorded a swarm of small to moderate earthquakes clustered along the same fault zones that would eventually rupture. The pattern was a cluster of deep events first, then shallower ones. Then a sudden quiet period of about 6 hours. Then the main shock. Scientists at the time didn't recognize the pattern because they had never seen it before. We recognize it now because we've spent 67 years studying what came before that night. When you take the seismic data from the last 72 hours at Yellowstone and you overlay it against the August 1959 sequence, the early shape of the curve is similar, not identical. The 1959 events were tectonic, driven by fault slip along the Hebgen and Red Canyon faults. The current events are happening inside the caldera itself, much closer to the magma chamber. But the rate of escalation, the depth migration, and the clustering pattern are following a curve that scientists have only seen one other time in the modern record of this volcano. That is why the observatory is paying attention. While the seismic story has been quietly building, the thermal story is the one that should make you sit up straight. Yellowstone has somewhere around 10,000 individual thermal features. Geysers, hot springs, mud pots, fumaroles. They are the surface expression of a hydrothermal system that runs straight down to the heat of the magma chamber below. When the heat source changes, the surface features change. They are the most reliable early warning system the observatory has, because they respond to deep changes faster than the ground can deform. In the past week, the Yellowstone Volcano Observatory's thermal infrared cameras have captured a 12% rise in average discharge temperatures across the major geyser basins. 12% does not sound like a lot. In a hydrothermal system this large, 12% in 7 days is enormous. It means heat is reaching the surface faster than it normally does, which means either the plumbing has changed or the heat source itself has gotten hotter. At Norris Geyser Basin, the hottest and most chemically active basin in the park, water temperatures in 3 separate features have climbed past their historical maximum readings. At the Mud Volcano area, near the eastern edge of the caldera, ground temperatures around the existing fumaroles have risen sharply enough that the surrounding soil is now too hot to walk across barefoot. Park rangers have quietly closed 2 unmarked backcountry trails in that zone for the rest of the season. That closure is in the official park bulletin, but it's listed as thermal hazard reassessment, not as anything more dramatic. At Old Faithful itself, the average eruption interval has shifted by about 90 seconds over the past week. Old Faithful is supposed to be one of the most predictable geysers on Earth. 90 seconds of drift in 7 days is the kind of change that geophysicists notice and write internal memos about. Take all of those readings together, and you get a system that is releasing more heat at the surface than it was last month. There are only 2 ways that happens. Either the underground plumbing has rerouted itself, opening new channels that bring hot water to the surface faster, or the heat source at the bottom of the system has intensified. Both possibilities point in the same direction. Something has changed below the caldera floor, and the change is significant enough that the surface is reacting. When most people hear that the United States Geological Survey has upgraded Yellowstone's monitoring state, they assume it means the public alert level has changed. It hasn't. The official volcano alert level for Yellowstone is still listed as normal color-coded green, just like it has been for years. That has not been raised, and the observatory has been very careful to communicate that nothing about the current activity meets the threshold for a public alert change. But internal monitoring posture is different from public alert level. The observatory operates on a tiered system of attention. Most of the time, monitoring runs on a baseline schedule. Stations report in, data gets reviewed once a day. Anomalies get flagged in weekly internal reports. When something unusual starts happening, that schedule compresses. Data gets reviewed every 6 hours, then every hour. Additional staff get called in. The deformation network, which uses GPS stations to measure ground movement down to the millimeter, gets queried more frequently. The gas sensors at the major thermal features start running continuous sampling instead of intermittent. Over the past 72 hours, all of those things have happened at the Yellowstone Volcano Observatory. Now, the internal monitoring posture is now at what they call elevated review status. That posture also activates something else that doesn't usually get talked about: evacuation scenario modeling. The observatory works with the National Park Service, the state of Wyoming, and federal emergency management agencies on a set of pre-built response models. Those models cover everything from a localized hydrothermal explosion at a single geyser basin all the way up to a caldera scale eruption. The models exist on a shelf, the way a fire department keeps a hose. You don't pull them down unless something tells you that you might need them. This week, 3 of those scenario models were quietly pulled down and updated. The smallest one covers a hydrothermal explosion at Norris. The middle one covers a moderate volcanic event with localized ashfall. The third one is the model nobody wants to talk about. It covers a large-scale caldera unrest event, the kind of thing that would require evacuating significant portions of 3 states. The fact that it was updated this week is not a prediction. The observatory updates these models periodically as a matter of routine. But the timing is the part that matters. Updating the largest model in the same week, the seismic and thermal data are spiking, is the procedural equivalent of checking your seatbelt right before the road gets rough. To understand what could be driving all of this, you have to picture what's actually under Yellowstone. Most people imagine a giant pool of molten lava, like a swimming pool full of fire, sitting just beneath the park. That's not accurate. The Yellowstone magma system is a vast, sponge-like body of partially molten rock called crystal mush that extends from about 5 kilometers below the surface down to almost 50 kilometers. Only about 10 to 15% of the upper chamber is actually liquid at any given time. The rest is hot, plastic, semi-solid rock that can deform and flow on long timescales but doesn't behave like lava. When that system goes through a period of unrest, it usually means one of 2 things has happened. Either fresh magma has injected from deeper in the system into the upper chamber, the way water flows from one tank into another, or the existing magma in the upper chamber has started to release dissolved gases as pressure changes. Both of those processes generate the exact pattern of deep, low-frequency earthquakes that the network has been recording this week. Both of them also push hot fluids into the hydrothermal plumbing above, which is why the geysers are running hot. Above the magma chamber, 2 large blocks of crust called the Sour Creek Dome and the Mallard Lake Dome have been quietly rising and falling for decades. They're called resurgent domes, and they are, in a sense, the lid of the system. When the magma below pushes up, the domes inflate by a few centimeters. When pressure releases, they deflate. The GPS network on top of those domes is one of the most precise deformation monitoring systems on the planet. And over the past week, the Sour Creek Dome has shown a small but measurable upward shift. Not catastrophic, not unprecedented, but noticeable and consistent with the rest of the data. When you put the seismic data, the thermal data, and the deformation data together, the picture they make is of a system that is doing something. not erupting, not collapsing, but moving in a coordinated way that the surface and the depths are both registering. That coordination is what makes this episode different from a normal Yellowstone fluctuation. Normal weeks have one of these signals firing at a time. This week, all three are firing together. So why does the next 96 hours specifically matter? Because that is the window in which the observatory will know whether what's happening right now is the leading edge of something larger, or whether it is going to settle back down into the background, the way Yellowstone has done dozens of times before. The way scientists watch this kind of episode is by looking for three specific failure thresholds. The first is sustained escalation in earthquake count. If the rate keeps climbing past the current numbers, especially if larger magnitude events start mixing into the swarm, that tells the observatory that the pressure event is not relieving itself. The second is migration of earthquakes toward the surface. When deep events start being followed by shallower events along the same vertical column, of course that means whatever fluid or gas is causing the pressure is moving upward through the rock. The third is acceleration of ground deformation. If the GPS network shows the resurgent domes inflating faster instead of plateauing, that means the source of the pressure is not just present, but actively growing. If any one of those three thresholds is crossed in the next 96 hours, the public alert level will be reviewed. Crossing a threshold does not mean an eruption. Yellowstone has crossed monitoring thresholds before in 1985, in 2003, in 2008 to 2010, and the system relaxed each time without producing anything dramatic at the surface. The vast majority of unrest episodes at large calderas end without an eruption. That is the most important context to hold on to here, but most is not all. And every time a system like Yellowstone goes through one of these episodes, the data the observatory collects becomes part of the model that decides what normal looks like. This week's data is going to be part of that model for the next century. Whatever happens in the next 4 days is being recorded with the most precise instruments humans have ever built and pointed at this volcano. That is the part that makes this episode different from the past 60 years of Yellowstone watching. The instruments are finally good enough to see the small signals. The catalog of past episodes is finally long enough to compare them. And for the first time since 1959, the pattern of the early signals matches an episode where Yellowstone genuinely changed. If you want to follow this episode in real time, the things to watch are publicly available. The Yellowstone Volcano Observatory publishes daily activity updates and posts the raw earthquake catalog on the University of Utah Seismograph Station's website, which has hosted the Yellowstone network for decades. The deformation data from the GPS stations across the caldera is also public, updated continuously, and you can see for yourself whether the Sour Creek Dome continues to move upward. What you want to see, if you want this episode to be a routine fluctuation, is the earthquake count flattening out over the next 2 to 3 days. You want to see depth staying clustered or slightly deepening rather than migrating upward. You want to see geyser temperatures stabilizing instead of climbing. You want the resurgent domes to plateau and then slowly deflate. That is what a normal Yellowstone unrest episode looks like in its declining phase, and it is by far the most likely outcome. What you do not want to see is the earthquake count continuing to rise past current levels, particularly with shallowing depths. You do not want to see new thermal features appearing in places where there were none before. You do not want to see the deformation network showing accelerated uplift in the central caldera. And any of those would be the kind of signal that prompts the observatory to upgrade the public alert level from normal to advisory, which is the next step in their 5-tier system. The honest answer is that nobody on Earth knows which of those two paths the next 96 hours will take. Not the observatory, not the academics who have spent careers studying this volcano, not the supercomputer models running simulations on the latest data. Yellowstone is the most studied caldera on the planet. And even that is not enough to predict what a system this large is going to do over a 4-day window. What we have is the data, the historical comparison, and the procedures of the people whose job it is to watch. What's happening right now at Yellowstone is not an eruption warning. It is not a prediction. It is a moment of unusual coordination across 3 separate monitoring systems, occurring at the same time. The United States Geological Survey has changed how closely it is watching the volcano. The 1959 comparison is not destiny. It is context. And the context says that the next 4 days are the kind of observation window that scientists will be writing papers about for decades, regardless of how it ends. The most likely outcome, by a wide margin, is that the swarm relaxes, the geysers cool off, the domes plateau, and Yellowstone returns to its background hum. That is what almost every unrest episode in the modern record has done. The least likely outcome, but the one that exists in the model on the shelf, is that this is the leading edge of a larger reorganization of the system. The kind of event that has happened at Yellowstone many times in the deep past and could happen again at any point in the next few thousand years. What sits between those two outcomes is the next 96 hours of seismic readings, thermal measurements, and deformation data, watched continuously by the observatory in Wyoming and analyzed in real time by every volcanologist on Earth who has access to the feed. By the end of the week, we will know whether this episode was a footnote or a turning point. If you want to follow the rest of this story as it develops, the next video on this channel goes deeper into the 1959 Hebgen Lake earthquake itself. The night it happened, the people who were there, and the lessons it taught the world about supervolcanoes. Watch it next, because the story of what happens at Yellowstone in the next 4 days starts there. Subscribe so you don't miss the update when the observatory's full assessment is released.